In this video, we continue our series about computer organization and design, and we're going to start working with OpenGL. OpenGL is a software interface that allows a programmer to communicate with graphics hardware. Since we're learning how computer is organized, we can use OpenGL library to experiment and see how software interfaces with graphics hardware. Well, to get started, we need to familiarize with some common terminology and basics aspects in graphics. So this is our today's presentation, Introduction to OpenGL. So I'm listing here some of the popular tutorial on the internet. You may find other tutorials as well. And of course, if you have any questions or if you'd like to share your ideas, you're welcome to post on the discussion forum, and hopefully we all be able to participate. So this is our common terminology. Rendering is the entire process of drawing an image to the screen. And basically we start with some sort of geometrical shape, geometrical model, or a mesh, and the process of rendering makes it visible on the screen. So a vertex is a single 3D point, XYZ point, in 3D space. So obviously here there's an example of a cube in 3D space, and here we have these places here are vertices. So generally we have here distinct vertices that would define our cube, right? So these are vertices right here. All of these are vertices in 3D space. Face most often is a 3 vertices forming a triangle. So what it means is that basically if we see this side of the cube, it is formed by 2 triangles. So basically this face of the cube or side of the cube is formed by 2 triangles, because OpenGL supports faces that are triangles. So triangle is the basic unit of making graphics visible in 3D space. So then we have transformations. So the transformations is moving one or more vertices in 3D space. So typically, if we have a specific geometric shape, then we would probably move it in, in uniform manner, so that all vertices are rotated in a similar fashion. Translation is simply moving vertices along X, Y, or Z axis. So here I can move my cube away from the view and even make it disappear, or bring it closer. So this is translation in space when we're moving it. Rotation obviously is that's something that we already discussed. We can rotate this cube the way we like, and that's the kind of transformation that represents rotation. Scaling, of course, is making it bigger or smaller. So this is not actually moving in space, it just shrinks or inflates right now. This is basically scaling, increasing and decreasing the distance of vertices from their center. Of course, somewhere we have a center of this 3D shape, and we can do this type of manipulation. Modeling matrix. This is a mathematical structure for holding transformations. Essentially, what happens at the beginning is that we choose a specific system of coordinates. Right? So somewhere we have this X, Y, Z, the axis that we choose. And we decide how we're going to design this geometry. And we could basically pick, like, most likely we're going to originally place the geometry close to the origin of the system of coordinates. So this being y, and this is z-axis, and this is x-axis, and we can design this cube like this, right? So we can put it somewhere like this and place it close to the origin of the system of coordinates. And then what we need to do is that when we're rendering it in 3D space and make it visible, we'd like to choose our rotations. We'd like to choose our transformations like scaling, making it bigger or smaller. So what needs to happen is that this geometry, this original geometry, has to be transformed. And this transformation from the original geometry to the actual positions and sizes in 3D space typically is represented by something we call modeling matrix. This modeling matrix holds together translations, which are moving in space, rotations, and scaling, which is making it bigger or smaller. So all of this is encapsulated in a it's like two-dimensional array, the matrix of values that allow mathematically define these types of transformations. We also have something that we call a view matrix. So the view matrix is another matrix that represents our observer in 3D space. Basically, this is our 3D world that we're looking at. And right now, the position of our eye is right in front of our screen. However, the observer could move somewhere else. So if this is my eye here, I could start viewing this box from a different position, right? Or I can move somewhere else. And I can move right here and look down this way, and so forth. So the observer can also move in 3D space. And because of this, we have another view matrix, which basically the idea of the view matrix is to bring the observer's eye into the origin of the system of coordinates. And that's the view matrix. So this would make it possible for the viewer to see this 3D world, the entire scene that we built from a specific position in that world. Projection matrix, of course, is getting 3D scene projected into a small unit 1 cube, but in reality, for the effect of the effect of the observer is that we have the perspective also that you can see that we have this not orthogonal projection, but we have a more or less realistic view of perspective as well. So anyway, when the projection is applied, we're actually fitting the entire world that we built into 1 unit cube. And then the rasterization finalizes the rendering, and the actual pixels are drawn on the screen.